Okay, we're going to talk about trying to define what a derivative is and when we take a derivative, what we're actually doing. Um, Differential calculus is basically finding derivatives of various things, and we're talking about curved graphs. We're no longer talking about straight lines and so on. So we'll quickly run through the slope of a line. We all know how to take the slope of a line, and we know that it's the change in y over the change in x, and we can do rise over run, and we can get the gradient of a line at between 2 points. And that's just basically calculating a rate of change. Well, derivatives, finding derivatives is exactly the same. It's a rate of change finding the slope. The trick is, at this point, is that you're doing it of a curved surface or a line as opposed to a straight line. And that brings a whole bunch of special problems to it. But so we'll take a look at how we find basically the gradient of a curving line, because we know that the gradient is changing at every particular moment in time along that curve. So what we do is we start off looking at what we call a secant line. A secant line is just a line that you create 2 points on a curve, and you just draw a straight line down through those 2 points. And that line that you create is called a secant line. Now, it's not a big deal to find the gradient between those 2 points. You can just do, again, the change in y over the change in x. It's a rate of change. And let's just say, for example, if the most common example is dealing with velocity or speed. So down the y-axis you have distance, and across the x-axis you have time. And so in this case, it might be that you're finding over an hour how fast you're traveling, if that's the time interval between the two dots. And so it's giving you an average rate of change between those 2 points on that curve. But again, we don't want an average rate of change. We actually want a rate of change at a particular point, at an instantaneous moment of time along that curve. We want to know what the rate of change is. And so this is what we do. This is what doing a derivative is. It's when we have that secant line drawn along the curve, what we do is we have those 2 points, and we know that that distance between x0 and x1 could be an hour. So we know that at this point we can calculate the change in y over the change in x, the speed that you're traveling in an hour. But we're going to bring those points closer together. And we're going to bring this f of 1 of x1 closer to f of x0. This initial point, basically, this is our initial starting point. We want to know what the rate of change at that point is. And so we just keep making that point closer and closer and closer. And you can see that as we bring this point above closer to the initial point, our change in x is going to get smaller and smaller and smaller until it begins to approximate 0. So that space between those two dots gets infinitely small. Now, what does that look like? Well, if you take a look here, when you take a graph and a curve and you zoom it in, what eventually happens, if you zoom it in far enough, that you're going to get pretty much a straight line. So as we get those 2 points closer and closer, infinitely close to each other, they're basically now kind of creating a straight line. And so now at that point, we can draw what we call a tangent to that point. Right on that point, we can draw a tangent line. A tangent line is just a line that hits a curving surface at one particular point. So we brought those points now closer together. We now have this, we can create a gradient. If we can create now a gradient along that point, basically, because we've brought those 2 points so close together now that we can actually draw a line that sort of goes through them, and if we can find the gradient of that tangent, we have then found the rate of change at that instantaneous moment in time, whatever it happens to be. And that's what a derivative is. It's about finding that gradient of that tangent line and figuring out what that rate of change is in that moment of time along that curve. And the reason that we can do that is because we bring those points closer and closer together till we get them pretty much on top of each other. We're approximating that distance between them to be 0. It's infinitely small. And at that point, we can draw a tangent to that curve, find the gradient of that tangent, and at that point, we've done a derivative, we can find what the instantaneous rate of change is in that moment.